In this particular lab, we observe an object moving at a constant velocity for a stated amount of time. Using video of this object in motion, we then place it into a software called Tracker and convert this observation into position versus time points along the x-axis of motion. From there, we plot both a predicted and actual set of position versus time plots, and then compare the two using several of Newton's laws of motion. In my particular experiment, I observed that the position versus time graph of my object in motion was linear to upward sloping. Unfortunately, while the theoretical model was completely constant, my actual model did not reflect this. This entire model relies on two of Newton's laws of motion. The first one being Newton's second law, that the force is proportional to the mass and acceleration of the object. The second important law which we utilize in this model is Newton's first law, that of inertia. All objects persist in a state of rest or uniform motion unless an external force acts upon it. In our model, we are assuming that the ball is moving at a constant velocity and that it has a net force of zero. Thus, the acceleration is also going to be zero. More on that in a few minutes. We rely on several assumptions in order to do this experiment. The first one being that the initial velocity, 1.009 in the positive x direction, remains the velocity throughout the entirety of the observation. The next thing that we assume is that the initial time is at time 0. In other words, we're observing it at 0 seconds. Finally, we have the final time being at 0.934 seconds, the time which the video ends. And lastly, we assume that the net force is 0 throughout the entirety of the observation. In other words, the velocity remains constant throughout the entirety of the observation. One of our assumptions is that the force remains constant throughout the experiment and that it is 0. Thus, 0 over a mass, which we've already specified, is going to equal an acceleration of 0. As a result, our final velocity must be equal to our initial velocity. Currently on the screen is a plot of my position versus time values, both in the actual experiment that I did and the calculated experiment. You can observe from this graph that the calculated position was entirely linear and moved at a constant rate. In this particular experiment, I observed a ball moving in the positive x direction. I then placed that video into the software called Tracker, where I was able to place several points in position and relate it to time in order to get a time versus position graph, which can be seen here. The points that were taken from this video and from Tracker can be observed in the ball versus experimented calculated velocity as the experimental velocity. Each of these represents a point in time and position, which was observed by the Tracker software. Some of the basic parameters of the computational model can be found here in the code. As you see, we have here that the ball is a sphere. We have some of the basic colors. And as we go down, we also have the ball's mass, which is that of a standard basketball of 0.625 kilograms. Here, we can observe some of the basic parameters that have been put into the code. Here we have the ball's mass, which is 0.625 kilograms. We also have the ball's initial position, which was found using Tracker. It can be seen here at time 0 and the x position here. Next, we have the ball's initial velocity, which was calculated using the first and second position and the first and second time. Here, we have the initial time, which happens to be time equals 0 seconds. Next, we have here delta t, the change in time, which is represented here by 0.01. Here in our code, we observe the ball moving in the x direction for about 0.9 seconds, just short of 1 second. Here, we assume that the net force is 0, because we assume that the acceleration is also 0, and that the ball is traveling at a constant velocity. Finally, we can run our program and see a computational version of our ball's observed motion. As you can see, the graph here illustrates the calculated position versus the time. Looking back at our original calculated versus experimental graph, we can see that same plot illustrated here versus the experimental velocity here. As you can see, the experimental velocity in actuality was not constant and actually tended to slow down. To avoid this in future experiments, a greater force should be applied in order to make sure that the ball is actually moving at a constant velocity throughout the entirety of the experiment. This particular experiment illustrates Newton's second and first law very plainly. In our particular circumstance, we assumed that the force was equal to 0 and that thus the acceleration would be 0. As a result, we assumed that the velocity for the final velocity would be equal to the initial velocity. However, in our real experiment, we saw that this was not the case. One takeaway from the experiment is that an object can have a 0 acceleration and still be moving. In other words, the velocity of that particular observation remains constant throughout the entirety of the experiment.